So welcome to the third video in the Ramachandranplot series. As usual, we will do a little bit of recap of whatever we studied in the previous video, and then I will continue from here. So if you look at the Ramachandran maps which I had shown earlier, superimposed with the phi-psi conformations taken from the protein databases, we do find a majority of the protein phi-psi conformations are within the allowed regions. However, there is quite a significant fraction over here, here, which are outside. The reason for that we had seen is due to the glycine amino acids. Now, glycine, which lacks a C-beta carbon like the alanine, therefore, it misses out certain clashes which the C-beta carbon would have done. And so therefore, the glycine map, as you can see out here, has an additional allowed regions. And some of these points that were there, these are actually due to glycine residues. So in fact, if we remove the glycine residues from our data set, and then if we plot them again, what indeed we find is that majority of the points now, the bulk majority, are within the allowed regions, and a very few of them are still outside, of course. And there are some here, for example. This looks like another cluster here, another cluster here, which are still outside. And we have to find an explanation, and for this, and also some in this region also. So we have to find an explanation for these, because now that the glycines are out, we don't have an easy enough explanation why these amino acid conformations are outside the allowed regions of the map. So there can be various reasons for this, and let us look at them. The number one reason, of course, that these are errors in structure determination. Now you have to understand that these points, all these points which have been taken out here, are from experimental data, right? These are all from the steric lines, of course, are calculated from theory, but all the points, the shades, are from experimental data. And of course, like all experiments, there is one thing common between all experiments, that there are always some experimental errors, right? So it is quite possible that a few of these structures are wrong, right? So, and we have to be aware of the possibility of experimental data. And it is also critical we understand that why these errors were made. So what kind of problems in the experiments, particularly X-ray diffraction experiments, that causes errors of model building, and thereby residues go into the disallowed regions. To understand that, let us take a pair of crystal structures and what do we get out of that. So here is an example of a protein whose structure code is 5GY7. This in fact was solved by one of your seniors, Dr. Nupur Singh, here in SBT. And now what happens in X-ray crystallography is that you do not actually get very nice protein models of the type we have discussed here. So these pictures are nice, but these do not come out of the experiment. In fact, what we get in the experiment out here is looks something like this. If you see carefully out here, you see some blue blob-like regions around here, right? So these are the so-called electron density of the protein. So this is what you actually measure. And then what you have to do, the experimenter, in this case Dr. Nupur Singh, what she did is that she interpreted this electron density in terms of a chemical model. And as you can see this with the stick and ball representation. So you can see, for example, that she saw an electron density which looked more or less like a twisted pentagon. And she realized that this must be a proline residue. And when she placed the proline residue out here, it was fine. But this is her interpretation, right? And interpretation can, of course, supported by the experimental data, which is this electron density points. Now, in this particular example, the electron density is so nice and clear that it wasn't actually very difficult to model this. And so Nupur could correctly model the electron density throughout the protein. And the end result is this is the Ramachandran map she got. Now out here, the black points, they represent non-glycine amino acids, while the glycine amino acids are shown by white dots out here. I hope you can see them in the video. Now you know that glycine has an additional allowed region. So if you see the green regions out here, these mark the additional allowed regions for glycine, while the brown region marks the allowed regions for non-glycine residues. So of course glycine can be there in both the sides, and you do see some of the glycines in the green region which are only specifically allowed from there. But much of the non-glycine residues, I think excepting maybe one out here and one out here, these are well within the allowed regions of the Ramachandran map. So this is what one expects from a well-solved structure like the one which Nupur solved. But if you look at another structure, this one I just picked out from the database. Again, it has its code is 2GUW. And here if you see, the electron density is very patchy. So it exists, some blob which is unrecognizable. You cannot just make out like what is that amino acid. And it is not there in most other places. So when in such kind of cases, this may happen because the crystal may not be very good. Usually that is the main reason that the crystal is not of high quality. Sometime during the data collection, that is when the X-rays are being bombarded into the crystals undergo damage because the X-rays, they produce something called Auger electrons, and these can damage the crystal. And there are various other reasons also. So anyway, whatever be the reason, the crystal wasn't probably very good, or the data collection had problems or whatever. So we see very patchy electron density, and interpreting them becomes very, very difficult. And when you do this, when you still try to interpret them, you make mistakes. And you can see that in the Ramachandran map. So you see quite a lot of amino acids are clearly in disallowed regions out here. Some of these non-glycine residues which have come in regions out here which are exclusively reserved for glycine. So no non-glycine can come out here. And some of them are really totally out. So where glycine or any other amino acid cannot exist. And you find a large number of such possible errors. So these kind of things, of course, all of this data is there in the databases, which went on to make this plot out here. So obviously, this sort of errors are going to contaminate the database, and which is going to create problems for further analysis. In fact, nowadays, it is mandatory for us that we have to validate the structure that we have determined by crystallography. And one of the most important tools of validation, in fact, is the Ramachandran map. So whenever a person solves or determines the structure of a protein using X-ray crystallography or even NMR spectroscopy, it becomes important to plot the Ramachandran map. And if one sees a Ramachandran map like this, where a significant number of residues are out in the disallowed region, then we know that something is wrong, and we take another look at the experimental data. But when we get something like this, where the vast majority of the amino acids are deep inside the allowed regions, then we know that everything is fine, and then we can go ahead and deposit our structure in the database. So, of course, the number of absolutely wrong structures in the database are now very little, because this kind of validation using the Ramachandran map and also other tools have now become a standard practice. But some of the older structures which were there, which have been deposited maybe about 20-25 years ago, those days the notion of careful validation was not so much there, and some mistakes have crept in, and these are there in the database and they remain. So one has to be very careful when studying X-ray structures data from the database. One should probably check it out once again by ourselves, to see that, okay, it is in a good shape and nothing is very wrong. So thereby we find that a major reason for why amino acids can move into the disallowed regions of the map is, of course, errors in structure determination. But even after taking care of them, even after removing those structures which are clearly wrong because of experimental reasons, we still find that there are a few residues which are in the disallowed regions. And I've given a reason out there that these are due to special interactions, which could be hydrogen bonding, metal bending, or whatever, which distorts the peptide geometry. Now, what exactly do we mean by this? And again, I would like to show you with one example. So here I picked up from the database a particular protein which goes by the structure code 10X. And what we see is that there's just one amino acid out here, which is there in the loop or turn-like region. This is in the Ramachandran disallowed region. In fact, this is the phi psi out here. Phi is equal to 39 degrees, psi is equal to minus 111 degrees. The amino acid was aspartate. It wasn't glycine. So clearly an aspartate cannot come out here. So that is a disallowed region. Now, why is it so? So firstly, we have to really check things out. So what I did is that I picked up the phi psi from the particular crystal structure, and then I modeled an alanine dipeptide with the same phi size. So when I do that, what I find is that indeed there is a short contact between the C beta atom and the nitrogen, which has a distance of 2.6 angstrom. So my model is telling that there should be a short contact. But in the crystal structure, when I measured the same distance in the crystal structure, I find that it is 2.8 angstrom. It's a very slight difference, but that's the difference it needs, because the extreme limit for a carbon and nitrogen is around 2.8 angstrom, and you can check it here. So if you see, the extreme limit for a carbon and a nitrogen is 2.8 angstrom. So that's the limiting distance which is just about allowed. So what happens out here is that by some reason or the other, this distance is larger. Now, how do I explain this? My model says that the distance should be 2.6 angstrom, but the experiment says the distance should be 2.8 angstrom. The answer lies is actually the geometry of the peptide between the model which I did and the experiment is slightly different. So for example, the bond angle in the C alpha, around the C alpha region, something we call the tau angle. So this here in my model structure was 111 degree. But in the experimental case, the tau angle is 116 degree. Similarly, the bond angle in the carbonyl carbon in my model structure was 114 degree, and this is 122 degree. Now these values, 111 degree, 114 degree, these correspond to the geometry of the peptide, which was observed from Ramachandran himself, which was given by Ramachandran himself by a statistical analysis of a lot of well-solved crystal structures. So these are the most common values that one finds. But in this particular case, this particular bond angle is clearly a little bit deviating from what is normal. While the normal value is 114 degree, here it is significantly larger. It's about 122 degrees, and also the tau angle is a little bit larger, right? So what I could do then I took this geometry, I took the peptide geometry from the experimental structure, and I calculated another Ramachandran map. And the red contours are this new Ramachandran map, while the black contours are by standard Ramachandran map. And what I observed, that indeed a new allowed region has opened up in this place, and my amino acid is just about making it, right? So clearly this tells that sometimes what happens, one has to understand one thing, that even the Ramachandran plot, the way it has been calculated, is based on certain assumptions. And what were the assumptions? The assumptions were on the peptide geometry, which was used by Ramachandran to work out his map. And that is the bond lengths and the bond angles, etc. for the alanine dipeptide molecule. So what he did is that when he constructed the alanine dipeptide molecule, so he used certain bond lengths and bond angles out here, right, to make this. And these he obtained by a statistical analysis. These are the average values he obtained from statistical analysis of crystal structures. Fine. So there's nothing wrong with the assumptions that he made. But what happens that in some cases, those assumptions are violated. So in some cases, in some specific regions of proteins or peptides, it might happen that the bond angles, particularly the lengths, are more or less constant. So the bond angles deviate from the average values which are used by Ramachandran. And once they deviate, of course, the shape of the map will change. And in this particular case, it's changed in a way so that this particular amino acid comes into the allowed region. So the first and very important message out here is that the particular shape of the Ramachandran map, what you can see here with the black contours, it is not something written in stone. Okay, it can change a little bit depending upon the particular bond lengths or bond angles, whatever you have used in your alanine dipeptide when you are calculating that. And in actual crystal structures in some proteins also, because of certain reasons, and I'll come to it in a moment, these angles might change, and once they change, the shape of the plot can significantly change. So this might make an allowed region, it might make it disallowed, and a disallowed region can be made into allowed. And therefore, barring errors of structure determination and all that, the few cases that we find, often these refer to this strains or distortion in the peptide geometry, which is found in the experimental structures. And because of those distortion, new allowed regions or the additional allowed regions are created, and where these amino acid conformations are accommodated. So you can ask now that why is this strain, I mean, why is it happening and all that. So let's take our specific example of this particular model. So here what I have the same amino acid here. This is the aspartate, which was the critical amino acid which in the disallowed conformation, and I also plotted the nearby residues here. So what one observes immediately is that this entire region is covered by a lot of hydrogen bonds. There are 3 water molecules hydrogen bonding with this, and there are other hydrogen bonds with other amino acid, and also it occurs in a very tight turn region. So because of this sharp turn which is taking, already there are some constraints on the peptide structure, and therefore it has to be held by hydrogen bonds. And these hydrogen bonds have what it has done is that it has pushed and pulled the peptide structure a little bit. So some of the bond angles particularly are a little bit distorted, and because of this distortion, the Ramachandran map kind of changed, and this particular conformation now becomes allowed. But if we use the classical Ramachandran map to look at it, it will appear disallowed. So this is the thing. So now if we look at our database, and what is the explanation for residues which are not in the allowed regions? What is the explanation? In most cases, the explanation is that this is due to some sort of local strain in the protein structure, which has happened for some reason or the other. There might be different reasons. Hydrogen bonding is one case which I have showed you. There might be other reasons as well, but these are all local to that particular structure, to that particular protein, and which is why this disallowed conformation has become allowed. Okay. Now, is it very common to have strains in protein structure? Indeed, it's not very uncommon. In fact, very early on, in fact, Ramachandran himself observed something, that if you look at the tau angle, which is at the C alpha carbon atom, since it's a tetrahedral carbon, I would assume that the tau angle should be 109 degrees. Now, if we have calculated with 109 degrees, okay, one observes that in the middle of the alpha helical and the extended strand region, there is a certain region which becomes disallowed. So something like this region, which is now disallowed. In fact, Ramachandran called it the so-called bridge region. But the trouble is that even though this appears to be disallowed, but we see in the database that there is a lot of structures in the bridge region, right? So a lot of amino acid conformations are coming into the bridge region. So what? So Ramachandran at that point of time decided that this tau angle must be extended a little bit. And if we extend it to about 113, 114 degrees, then the bridge region disappears and it becomes allowed. So which means that now why is that bond angle to be extended a little bit? And that is obviously because of some local strain. So which means that many proteins which have amino acid conformations lying in the bridge region is already strained a little bit. So the tetrahedral carbon, which has a tetrahedral bond angle of 109.5 degree, is a little bit broadened, and it becomes about 114, 115 degrees. So overall, if I take the average of all amino acids, okay, then the average bond angle comes out to be about 110 degrees. But in this region, particularly when I see all the amino acid conformations in this region, they have the bond angle is about 114 or even sometimes as high as 115 degrees. So that means that for all the conformations lying in this region, which are part of an extended alpha helical family, and that there exists some strains. Now you know that alpha helices are hydrogen bonded between I to I plus 4 residue. So maybe that hydrogen bond has a role to play, or there might be other regions also, and which causes a strain in the bond angle to from 110 it moves to about 114 degrees, and thereby this bridge region becomes allowed. Okay. Similarly, in some places you would see that there is a region out here. Okay, so somewhere here, where an internal hydrogen bond forms, and even though it is otherwise disallowed, but because of that internal hydrogen bond, that becomes allowed. This was in fact discovered way back in the middle 1960s by Ramachandran himself. Later on, we have seen that some of the other regions, for example, so regions around this place, for example. So these, why these kind of distortions happen, people have worked it out. And almost all cases we find that the bond angles are a little bit twisted because of local strains, and that then these things becomes allowed. So that is the story of strains. So we see that a little bit change in geometry of the peptide can cause some changes in the Ramachandran map. Now there is one amino acid, okay, which has a very highly weird geometry. Of course, one of them is glycine, which lacks C beta atom, and there is also another amino acid, namely proline, which has a very strange geometry because it is a circular, the cyclopentane or pyrrolidine actually, because it has a nitrogen out here. The 5-membered pyrrolidine ring, it causes a certain constraint on the phi angle out here. Because of the ring has to close, the phi angle out here is is somewhat constrained in a certain region. So if you look at the Ramachandran map of proline, we find that it's quite different. These are all proline amino acids which are kept up here, and these are the only things allowed. Again, this particular region, there are certain distortions are allowed happen in the proline ring, so these become allowed in some cases. But by and large, proline removes most of the allowed regions and only a certain region, and mainly due to, if you can see, it is the standard map, but the phi angle is now restricted between about minus 50 to minus 100 degrees, and that is because of the ring closure constraint out here. Not only that, now proline itself has a strange Ramachandran map. Turns out that the amino acid, whatever be the amino acid, non-glycine amino acid, if it precedes the proline residue, even that has a different kind of Ramachandran map. So here is an example of the residue pre-proline. So here is proline, and the one which is towards the N-terminal side of that. Now here I've plotted a steric map, and you can see that the bridge region is missing and the alpha helical region is also a little bit smaller. If I look at from the database, the pre-proline map, I clearly see that the extended region is well populated, and very little in the alpha helical region, in the left-handed helical region, and some up here, also in the left-handed extended chain region. So this is because some constraints are placed by the proline to the residue prior to it. Okay, and that causes again a difference in the Ramachandran map. Now, one thing you know that in proteins, the proline residue has a role to play in breaking alpha helices. Okay, possibly one reason for this is this: that whenever you have a proline, the residue before it has very small chance of being in the alpha helical region. It's largely well, the extended region is well populated for proline. So, which is why perhaps that proline is a reasonably good helix breaker. We will talk about this aspect. This is important because when you are designing structures and you are building an alpha helix and you want to stop at some point, one good idea will be to place a proline residue there. And the reason is being this, that the proline disfavors alpha helix quite a bit. So now let us move to another special case, and again involving proline. is that when we discuss about the peptide geometry, we had always said that because of the delocalization out here, the peptide bond has a partial double bond character, and generally this is in the trans conformation where omega is equal to 180 degrees. Okay, but sometimes omega can also be around 0 degrees. This becomes particularly true when this NH is replaced by some other atom, a carbon, for example. In proline, for example, this H is replaced by carbon, and then it cyclizes this way. So in such cases, very often you will find omega is equal to 0. So so these things we call them cis peptides. Again, when it is something like 0, roughly we call it cis, though ideally we should call it syn periplanar. But anyway, so these cis peptides, majorly these are found around proline residues, but sometimes maybe about 0.1% of the time you find non-proline residues also, they have cis peptides. Now, obviously, if an important angle like omega, which has now flipped from 180 to 0 degrees, clearly you expect a change in the Ramachandran map. And here is the cis peptide Ramachandran map. In fact, surprisingly, it has more allowed regions. And of course, on the left side of the map, on negative phi regions, the positive phi regions is more or less gone. Okay, you hardly find anything out there. So most cis peptide residues, they come in the negative phi regions. Now, there is a narrow band out here, which is disallowed. Now, Ramachandran in one of his articles, he writes that if one adjusts the extreme limit by a very little amount, as less as 0.03 angstrom, 0.3 angstrom, then this also becomes allowed. So some people consider that they just join up the whole thing. They disregard this particular disallowed region. But if you are very particular about the extreme limits, then this will appear disallowed. Well, at least in one of his articles, Ramachandran considered it allowed by adjusting the extreme limit. So most of the cis peptides you will find that they occur in the negative phi side regions. So, and as I mentioned, majorly cis peptides are found in prolines. So earlier we had discussed quite a lot of the homopolymeric amino acids, and in fact we talked about our helices and all that sort of stuff. So one question one can ask at this stage that, okay, I mean, if I have a proline residues, a homopolymer of proline, then what kind of structure can I expect? And so here we have, turns out that there are two possible structures, and one of them, these are experimentally and observed also. One of them we called polyproline 1, where you have negative phi. Both of them, the phi size are nearly the same. And in this polyproline 1, omega is 0 degree. While the other one, polyproline 2, omega is 180 degrees. Now the phi size are more or less close to each other. I mean, with the psi being about plus minus 150 degrees, a little bit, and phi is fixed at minus 75 degrees. These are in the idealized fiber diffraction models. But just the shift in omega makes a major change. That the polyproline 2 structure, which has trans peptide bonds, this is left-handed. Okay, while the polyproline 1, which has cis peptide bonds, this makes a right-handed helix. And also you will see the polyproline 1 is a little bit fat helix, radius of around 2 angstrom, n is around 3.3, h is 1.7, while the polyproline 2 is much extended in a left-handed conformation, n is around 3 and h minus 3.1 because it's left-handed, and r is now less. Instead of 1.9, it has come down to 1 angstrom. So these are some of the aspects of unusual Ramachandran maps, and we had looked at the unusual Ramachandran map of the cis peptide, unusual Ramachandran maps of proline, and unusual Ramachandran maps of the pre-proline also. Of course, that is also not the normal case. And then, of course, the most important one, the unusual Ramachandran map of glycine. So in this lecture, we have seen some of the different kinds of unusual Ramachandran maps, and we had also discussed that why residues go into disallowed regions because of errors in crystal structure. In a good crystal structure, they are all very fine. In a not so good crystal structure, they are not very fine. and nowadays it is common for experimentalists, crystallographers, and NMR spectroscopists to actually check their structure, whatever they have solved, using the Ramachandran map. In fact, this in fact is a major development in around mid 1960s, when Ramachandran first came out with this idea. People were not very happy with it. There was a lot of skepticism. The reason being that when they plotted the phi size of some one or two protein structures which were known, they found quite a few of them are going outside the map, outside the allowed regions, and they said, "Oh, you must be wrong because it doesn't agree with the experiment." Now we know that the disagreement was not due to any mistake on the Ramachandran's part, but it was a mistake on the part of the crystal structure. In fact, that early hemoglobin structure is no longer there in the structure database, and that is known to be significantly wrong. Later on, structures have been better solved, better determined, and better modeled, and then one finds that everything is within the Ramachandran map. It was in the in the 90s when Gerard Claret and Alvin Jones from Uppsala University, they made a case that one could use the Ramachandran map to validate protein crystal structures, and they were very persuasive in their arguments, and in some of their papers, one of them called Phi Psychology is extremely important in this regard, and if you want I can give you the reference also. And after that, thanks to their arguments, now it is common practice for crystallographers and NMR spectroscopists to use the Ramachandran map to define, to validate their structures. And if they find a bad Ramachandran map, they know that maybe something is wrong with the structure, and then they go back to the experimental table, and then maybe they improve upon it, refine their results, or they do it again. So what initially the Ramachandran map was checked against crystal structure. Nowadays it is other way. The crystal structures are now being checked against the Ramachandran map. So I will stop here at this point, and in the next video lecture we will be talking about unusual amino acids, that is amino acids which are not found in proteins, and how they affect the Ramachandran map, and how we can use that to design predefined structures. So how we can use that to rationally design protein structure. That of course was the main theme, should have been the main theme of the talk, but we have to wait till the fourth video in the lecture before we come to that. So until we come to that point, let me wish you goodbye and stay safe.